In this lesson, I am going to discuss about the acid-base theory. There are three main explanations about this theory. The oldest one is the Arrhenius theory. It was proposed in 1887 by Sainte Arrhenius. So this is the most basic theory and easy to understand. According to this theory, a compound that can donate a proton in an aqueous medium is an Arrhenius acid. And a compound that can donate a hydroxyl ion in the aqueous medium is called as Arrhenius base. So let us explain that further. Let us take simple example. Hydrochloric acid. Hydrochloric acid ionizes to hydrogen ion and fluoride ion. So this will be in the aqueous medium. Now you can see hydrochloric acid produces a proton to the medium. Thus hydrochloric acts as an Arrhenius acid. Then we will go to sodium hydroxide, again in the aqueous medium. Sodium hydroxide ionizes to sodium ions and hydroxyl ion. So sodium hydroxide acts here as an Arrhenius base. The limitation of this theory is it can be applied only in the aqueous medium, and also it cannot be used to explain some species like ammonia. How do they act as bases? That means ammonia doesn't donate hydroxyl ion. It acts in a different way. So we have to use different theory to explain species like ammonia. Now we will move into the second theory, Bronsted-Lowry theory. This was introduced in 1923 by two scientists, J. N. Bronsted and Thomas Martin Lowry. According to this theory, a substance that can donate a proton is identified as Bronsted acid, and a substance that can accept a proton is considered as a Bronsted base. This is different from earlier theory we described, that is Arrhenius theory. In that Arrhenius theory, we considered proton donor and hydroxyl ion donor. But here we can only consider proton acceptor and proton donor. Another specific theory about this Bronsted-Lowry is the conjugate system that can appear in the aqueous system. Let us consider the dissociation of acetic acid in the aqueous medium. It will produce acetate and hydronium ion. Again, this is in aqueous medium. Here acetic acid can donate a proton and it forms acetate. Then we can identify acetic acid as Bronsted acid. Water accepts that proton and produce hydronium ion. Thus we can tell water acts as Bronsted base. This is a reversible system. In the reverse reaction, acetate ion accept a proton from hydronium and produce back acetic acid. Then this acetate ion acts as Bronsted base. Hydronium ion donate a proton, then it acts as Bronsted acid. Now we can apply the conjugate theory. Acetic acid and acetate ions are conjugated. So we can tell the conjugate base of acetic acid is acetate ion and conjugate acid of acetate ion is acetic acid. Similarly, water and hydronium ion are conjugated. Then conjugate acid of water is hydronium ion. Conjugate base of hydronium ion is water. So this is how the conjugate system works in Bronsted-Lowry theory. Now let us compare the two theories we described so far. Let us take hydrochloric. Hydrochloric can ionizes to hydrogen ion and chloride. This should be in the aqueous medium. Since hydrochloric donate proton OH plus, it can act as Arrhenius acid, and also it can act as Bronsted acid, because both those theory define an acid as a species capable of donating a proton. Similarly, acetic acid can dissociate in aqueous medium and produce hydrogen ion, let us say hydronium here, and acetate. Here also, acetic acid is capable of donating a proton. Then it can act as an Arrhenius acid as well as Bronsted acid. Now let us consider sodium hydroxide. Sodium hydroxide ionizes and produces sodium ions and hydroxyl ion. Medium should be aqueous. Now clearly we can say sodium hydroxide can act as Arrhenius base because it can readily produce hydroxyl ion. In the presence of acid, let us say HCl, it produces salt and water. This is simple neutralization reaction. Then we can say sodium hydroxide accept the proton provided by hydrochloric acid, something like this. So then this will produce sodium ion and water. Then we can say sodium hydroxide can also act as Arrhenius base because it can donate hydroxyl ion to the medium, and it can act as Bronsted base because it can accept a proton that is given by an acid. Let us consider ammonia. Ammonia in aqueous system accept a proton from water and form ammonium ion. Let us say this is aqueous medium. Because ammonia can accept a proton from water, it has acted as Bronsted base. But ammonia cannot produce hydroxyl ion to the medium like in sodium hydroxide. Then we can say it cannot act as Arrhenius base because Arrhenius base should be capable of producing hydroxyl ion into the medium. If you consider this reaction, even though it produces hydroxyl ion, ammonia has accepted a proton from water. As a result of that reaction, hydroxyl ions are produced. To become Arrhenius base, that species should be capable of producing hydroxyl ion directly to the medium.